Hello, I'm Sabrina Octaviani from Metallurgy and Material Engineering, and I'm going to present about polymer materials, mechanical properties. First, how the nature and spatial arrangement of monomer units within a polymer chain influence its flexibility, toughness, and tensile strength. First, the physical properties. As the chain length and cross length increase, the tensile strength of the polymer increase. Polymer do not melt and they change the state from crystallinity to semicrystalline. For chemical properties, compared to conventional molecule with different side molecules, the polymer is enabled by hydrogen bonding and ionic bonding, resulting in better cross-linking strength. Dipole-dipole bonding side chain enable the polymer from high flexibility. Polymer with van der Waals force, cross-linking chain, are known to be weak but give the polymer a low melting point. And optical property due to the ability to change their refractive index with the temperature, as in the case of PMMA and HEMA MMA, they are used in lasers for application in the spectroscopy and analytical application. For example, polyethylene. The simplicity of the ethylene monomer allow the produce of the polymer chain with varying degree of crystallinity depending on the polymer condition and the percent of branching. High density polymer has minimal amount of branching leading to higher degree of crystallinity and thus greater stiffness and strength and chemical resistance. The fluorine atom in the monomer create with a very strong carbon-fluorine bond, resulting in the melting point, excellent chemical resistance, and very low surface energy, which give PTVA its non-stick property. The strength of the CF bonds and the shielding effect of the fluorine atom also contribute to PTFA's notable thermal stability and low coefficient friction. Next, how does the percent of the very high molecular weight chain contribute to overall performance of material? First, it increase tensile strength. Chain have more entanglement and interact over a larger surface area through van der Waals force. This result increase tensile strength because the long chain are more difficult to pull apart, require more force to break the material. And the second is enhanced toughness. The length and entanglement of a high molecular weight chain allow the material to absorb and dissipate energy more efficiently. When force is applied, the chain can strengthen and deform, which help to prevent crack propagation and material failure, leading to enhanced toughness. The third is enhanced thermal stability. The long degree of the long chain degrade at a higher temperature, which mean they can withstand the higher processing temperature and have improved long-term stability under the thermal stress. Fourth is better stress crack resistant. The entanglement in HMW chain provide the barrier to this sliding, thus enhancing stress crack resistance. Five, increased viscosity in melt and solution. The more entanglement and interact over a larger surface area through van der Waals force, increase the tensile strength because of the long chain are more difficult to pull apart, require more force to break the material. Uh, Yang six, reduce flow and processability. High molecular weight polymer may require more energy to process and could have limitation in molding or forming the increased shapes. Seven, improve impact resistance. The material can withstand sudden impact or stress without fracturing, which is specifically important for application requiring durability and reliability under dynamic load. Next is variable crystallinity. HMW chain might have region that crystallize differently compared to lower molecular weight chain, affecting to material overall crystallinity and consequently properties. Next is how do linear branch and cross-link structure differ in the polymer response to mechanical strength. First is linear polymer. Linear polymer typically exhibit higher tensile strength and rigidity due to the strong intermolecular force and less free volume. However, they may lack flexibility compared to branch or cross-linking counterpart. Branch tend to reduce the crystallinity of the polymer because the branch disturb the close packing of the chain. This result in increased flexibility and lower tensile strength compared to linear polymer. However, branch polymer may exhibit better impact resistance. Cross-linking generally increase the material stiffness, strength, and thermal stability, but decrease the flexibility. Cross-linking polymer are less likely to flow when heated and more resistant to solvent and deformation. For example, the structure makes LDPA more flexible and less dense than HDPA, suitable for application like plastic bag and film wrap, where flexibility and ductility are desirable. And the next is sulfur cross-linking at during full conization enhance the rubbery elasticity and tensile strength, making ideal for tires or other application require durable elastic material. And next is high density polyethylene, is example of linear polymer with minimal branching resulting in high strength and their stiffness. And the next is cross-linking and elasticity. How do linear branch or cross-linking structure differ in the response to mechanical stress? For cross-linking and elasticity, the connection between the density of a cross-linking polymer and their elasticity involve the trait between enhancing rigidity and preserving the capacity to deform and revert to their original shape. A polymer with a lower density of cross-link find a middle ground, providing both elasticity and the ability to bounce back to post deformation, which make them suited for that demand both supplement and durability. And the next is effect on elasticity and stiffness. Greater cross-linking result increase the stiffness, causing the polymer to become less flexible due to the resistant chain movement. Minimal cross-linking maintain the stretchiness of polymer, enabling them to return the original shape. Conversely, a high degree of cross-linking lead to significant stiffness polymer that difficult to stretch, like epoxy resins. And the next is crystal structure and mechanical property. Impact of crystallinity on the mechanical property. First is tensile strength and modulus elasticity. The order molecular chain can bear the load more effectively. The strong intermolecular force in crystalline region make the polymer more resistant deformation, and decreased crystallinity or more amorphous result to lower tensile strength and modulus of elasticity due to the less ordered structure, which is easier to deform under stress. And the second is toughness and impact resistant. High crystallinity can sometimes reduce the polymer toughness and impact resistant. This is because the rigid order structure is less able to absorb and dissipate energy upon impact, leading to brittleness in some cases. Amorphous region, meanwhile, can enhance the polymer ability to deform plastic and absorb energy, which can increase the toughness and impact resistant. And last is impact on brittleness. Crystalline polymer high crystallinity often leads to increase the brittleness. The rigidity of the crystalline structure means that it can fracture more easily under the stress, as there is a capability for the material to deform before the breaking. This because the order arrangement lack of flexibility to accommodate significant strain. So the mechanical mechanism to contributing to overall mechanical behavior. First, energy absorption and dissipation. Morphous region can absorb and dissipate energy through chain mobility and deformation, providing a mechanism for toughing the material. Crystalline region, on the other hand, contribute the load bearing capacity of the polymer. And the next is crack propagation. In semicrystalline polymer, the interface between crystalline and amorphous region can act as a barriers to crack the propagation. Crack initiate in brittleness crystalline region can be halted or deflected by the more ductile amorphous region, enhancing the material toughness. And thermal transition. This thermal transition influence the mechanical behavior at different temperature, which amorphous region becoming flexible above the TG, or decrease crystallinity, becoming more flexible above TG, and crystalline region, higher crystalline, maintaining stiffness and it up to T. Next is ductile to brittle transition temperature, or DBTT. T1 is the transition of temperature at which fracture occurs at 100% ductile fibers. FTP is a fracture transition plastic temperature when drop in temperature because most of fracture change from the ductile to brittle. T2 is transition temperature where a fracture is 50% ductile and 50% brittle. T3 is average energy absorption of the upper shelf and lower shelf. Upper shelf used when the material absorb the maximum impact, whereas the lower shelf is applied vice versa. And T4 is temperature is at CF equals to 20 joule. T5 is 100% brittle, and NDT is nil ductility temperature. And for example, polymethyl methacrylate, known as acrylic or polygas PMMA, is a rigid transparent polymer with relative high TG. Polystyrene application require higher toughness, such as HIPS is used where the polybutylene rubber is bled with polystyrene to improve the impact of resistance. And next is and then next is gas transition temperature and mechanical properties. So in below TG or this in glassy state, molecular chain are essentially frozen and there has no little movement and resulted to high stiffness and strength, but very low ductility. The material has a brittle manner and can fracture easily under the stress without significant plastic deformation. At TG, uh, the polymers start to transition from a glassy to a rubbery state and change in the gradual softening as the chain began to have increased mobility. The marked decrease in stiffness and slight decrease in strength, while ductility start to increase and less brittle but more capable to deform plasticity. And above TG or a brief state, it has significant mobility, but they are not completely free-flowing, characterized by modulus of elasticity or low stiffness and moderate strength. The ductility of polymer increased significantly in this state, allowing the material to be stretched and deformed much more than in glassy state. And next is influence of temperature on elastic modulus and strength. And elastic modulus at low temperature, typically polymer in glassy state where polymer molecular chain are frozen and unable to move. In this state, the elastic modulus high at the materials behave in brittle manner and resist deformation. And next is as the temperature increase, reaching the glass transition temperature, polymer enter a rubbery region and modulus elasticity decrease sharply because the increase of thermal energy allow the polymer chain to begin moving and making the material more flexible. And the next is above the glass transition temperature, modulus itu decrease gradually with the temperature as polymer chains slide past each other and the material behave in more viscous and or rubbery and more rubbery manner. And next is tensile strength. Below TG, tensile strength is generally higher due to the resisted motion of the molecular chain. As the temperature approach TG, tensile strength decrease, and the polymer chain begin to have more freedom movement and reduce the material ability to resist deformation under stress. And next is above TG, the tensile strength continue to decrease with increasing temperature. The polymer behavior dominated by viscous flow of chain, leading to material to stretch more easily, but has lower maximum stress and it can endure before failure. And physical reason behind the change is first intermolecular first. As the temperature increase, the thermal energy overcome the van der Waals force between the polymer chain, allowing them to move more freely, and free volume. As the temperature increase, the free volume within a polymer also increase, allowing chain more space to move and rotate. And chain entanglement, well, this entanglement contribute to material strength by resisting chain movement. Increasing temperature allow chain to disentangle more easily, altering material response to stress. So the increases temperature makes the chain decrease also makes the strength decrease. And next is impact of thermal expansion of mechanical integrity and performance of polymer. So impact of thermal expansion is first developing the stress. Polymer composite are constrained and unable to expand to contract freely with temperature change. The thermal stress develop and makes the material natural tendency to change its dimension with temperature. And the next is dimensional instability. Due to their relative high coefficient of thermal expansion compared to ceramics, this can be lead to fit and tolerance issue in assemble application, affecting the overall performance and reliability of the product. And the next is differential expansion in composite. Polymer composite consisting of polymer matrix and reinforcing fibers can experience differential expansion due to the mismatch in the CTA between the matrix and the reinforcement. And it makes the micro cracks, delamination, or even macroscopic deformation compromising the composite structural integrity and mechanical performance. And next is strategy for mitigating. First is material selection. You have to use low CTA polymers with inherently low coefficient of thermal expansion and can minimize the dimensional change and stress induced by temperature of fluctuation. And the next is design consideration, allows allowance for expansion, designing the component with allowance for thermal expansion and can prevent the build-up of stress and can include the use of expansion joint, flexible mount, etc. And next is thermal management, implementing cooling or heating system to control the temperature or reduce the rate of temperature change can help manage the thermal stress. Next is high temperature behavior of polymers. Behavior of polymers at high temperature normally is in decrease in viscosity. As polymer approach melting temperature, they transition from gassy or semi-crystalline solid to more fluid state, and decrease in viscosity lead to challenge to processing and application, and lost mechanical strength near above the TM or melting temperature. Polymer lose their mechanical strength and stiffness. The lost structural integrity can limit the use in loading bearing application. And next is thermal degradation. As temperature exceeding in melting point, polymer may undergo the thermal degradation, and this process break down the polymer chain, resulting lost mechanical properties, discoloration, and the release to volatile compound. And next is mechanical challenge at high temperature. First is structural integrity. Maintaining structural integrity is a significant challenge for polymer at high temperature as the material becomes softer and less capable of supporting loads. Dimensional stability. High temperature can cause expansion, distortion of or warping of polymer component, affecting their dimensional stability and tolerance fit in assemblies. And the last is thermal oxidation. Exposure to high temperature, especially the percent of oxygen, can lead to oxidation, further degrading of polymer and reducing its mechanical performance. Thank you so much, and I'm sorry if there's any wrong spelling or wrong and or typo. Thank you so much, and have a nice day.